new topic is exact differential equations. Let's start by an example. So we have this ODE that is 2x plus y squared minus 2xy times y prime equals to 0. At first glance, it's not linear because we have the term y prime and the term y second. It's not separable because things are all mixed up together. So none of the techniques we have developed until now is going to help us. But if you squint at this quite carefully, what you notice is that if you build a function psi of x and y, that is x second plus xy second, the derivative with respect to x of psi is the block we have at the beginning of the ODE, that is 2x plus y squared. While the derivative with respect to y of psi is 2xy, that is the term we multiply y prime with. Then let's just replace inside our ODE these two derivatives that we just built of psi. We have d psi over dx plus d psi over dy times dy over dx equals to 0. That means that the full derivative with respect to x of psi computed at x and yx is equal to 0. This means we can integrate it. The psi computed at x, yx equal to c for all values of x is a solution to our ODE. We call it an implicit solution in the sense that we don't have a formula written out for y. We still have to fish out y in some ways, but it is a solution of our system. What is the general form? How can we generalize this approach? We can look at ODEs of the form mxy, where m is a function of two variables, plus nxy times y prime equal to 0. This is very general for first order ODEs. And if we can find a psi such as m is the derivative of psi with respect to x, and n is the derivative of psi with respect to y, then we can rewrite the ODE into the format we saw before, d psi dx plus d psi dy times dy dx equal to 0, and that is solved by psi computed at x phi x equal to c all the time. When does this sort of psi exist? This is a theorem that if m and n are continuous in a rectangular region, and we also want the derivative with respect to y of m and the derivative with respect to x of n to be continuous in the same rectangular region. We want x to be spanning between alpha and beta and y to be spanning between gamma and delta. Then the ODE we just saw, m times ny prime equals to 0, is called exact differential equation, and it can be solved as we saw it if and only if the derivative with respect to y of m is equal to the derivative with respect to x to n for all x and y in the rectangular of continuity. Why is that what we want? Well, the general idea boils down to the fact that if we take psi, doing the derivative with respect to x of the derivative with respect to y of psi, or the opposite, that is the derivative with respect to y of the derivative with respect to x of psi, is the same thing. So if m is the derivative with respect to x of psi, and n is the derivative with respect to y of psi, when we mix derivatives up, we have to find the same thing. So if we take the derivative with respect to y of m, this is the derivative with respect to y of the derivative with respect to x of psi, that we can invert the order of the derivatives, is the derivative with respect to x of the derivative with respect to y of psi, but the derivative with respect to y of psi is n, so we have d over dx n. So reading the two extrema, we have the derivative with respect to y of m is equal to the derivative with respect of x of n. If this is not satisfied, then obviously there is no psi. Then there is an extra step to the proof, that is the fact that if this is satisfied, then psi exists. And we're not going to see that part. Let's look at an example. We have y cos x plus 2x exponential of y plus, parenthesis, sine of x plus x squared exponential of y minus 1, all of this times y prime equal to 0. By the notation we used before, the first block is equal to m. So we have m equals to y cos x plus 2x e at the y, and n being sine of x plus x squared e exponential of y minus 1. Does it work? Can we use the exact differentiation to solve this? Well, we take the derivative with respect to y of n, and we have cos x plus 2x exponential of y. We take the derivative with respect to x of n, and we have the same thing, so psi should exist. Must exist. So we have dy m equal dx n, so it exists a psi such as the derivative with respect to x of psi is equal to m, and the derivative with respect to y of psi is equal to n. Let's solve for it. So let's take the first thing. We have d over dx of psi equals something. That means that psi is equal to the integral of that something plus, with respect to x, plus anything depending on y only. Because anything depending on x is kept by the derivative, but we might still have some constants with respect to x that do depend on y. The same thing we do when we derivate with respect to y. We lose all the function of only x. So psi must satisfy both of these equations at the same time. It must be such that it's the integral of y cos x plus 2x exponential of y dx plus anything depending only on y, and also integral of sine of x plus x squared e exponential of y minus 1 dy plus anything depending only on x. If we do this, what we find is that we have y sin x plus x squared exponential of y plus a function of y equal to y sin of x plus x squared exponential of y minus y plus anything depending only on x. So you notice that the two sides have all the mixed terms of x and y that are the same, but the right side has a function of y that the left side doesn't have. So we have defined y as we check both sides, we pick everything, and we have y sin x plus x squared exponential of y minus y plus c, where c is any constant, because we only know psi through derivatives, so we know it up to a constant. But we don't care, we don't need that, we drop it. All the solutions of the ODEs are psi equals to a constant. So we have y sin x plus x squared exponential of y minus y equals to a constant k. And changing the constant k changes your solution depending on the initial condition. Here we look at this and we think of y being a function of x. For any value of x, we can find a value of y that satisfies this. But the solution is given implicitly, not as a formula of y. Sometimes you can enroll it in the function in a formula of y, but not always. As we did earlier on, we can also for exact differential equations use integrating factors. How does that work? Well, sometimes we have something that we would like to be an exact differential equation, m of xy plus n of xy y prime equals to 0, but m and n do not satisfy our requests. So what we want to introduce is we multiply everything by a new function mu that we can choose, and we want this new equation to be an exact differential equation. So what we want what we need in order to be an exact differential equation is that dy of mu times n is equal to the derivative with respect to x of mu times n. We can explicitly write it down as derivative of mu with respect to y times m plus mu m derivative of y equals mu x n plus mu nx, where the subscripts indicate derivatives. It might be hard to solve, but if you can, then you have a way to solve the exact differential equation. It also can have more than one solution, but in that case we don't care because we only need one version of mu that satisfies. So if you have the option of having multiple solutions, just pick the easiest one for you to work with, and you're good. So what are cases in which it gets easier? Well, we can assume that mu only depends on x. So the derivative with respect to y of mu is equal to 0. Then we come back to have an ODE actually. The derivative with respect to x of mu, that now only depends on one variable, is equal to mu y my minus nx, all divided by n, times mu of x. Now, mu only depends on x, so we need the center fraction to only depends on x. If that is the case, then we can solve the ODE and find a solution, any solution, and use mu back. Sometimes this assumption doesn't work. Maybe the opposite assumption works. So we can assume that mu only depends on y and not on x and do the same trick and hope to find a function mu that satisfies our requests.